Today, I don't want to start with matrices, self-attention equations, or query key value vectors, anything at all. Instead, we are going to answer a more interesting question. Why did transformers need to be invented at all? Because every major breakthrough in deep learning happened when researchers encountered a bottleneck, that is, a limitation, right? So, when they asked, can we remove this limitation? Can we actually remove it? So, the best way to understand transformers is historically, starting from feedforward neural networks, recurrent neural networks, LSTMs, GRUs, encoder decoder models, attention, and then comes the hero transformers. Think of this as understanding why each architecture was invented, because every step solves a weakness of the previous one. This is about a series of bottlenecks in sequence modeling and how each generation removed one bottleneck after another. That's why the transformer paper, Attention is All You Need, felt revolutionary. It wasn't merely a better neural network, right? It changed the fundamental assumption that sequences must be processed sequentially. And now we know where it started every time. Can we remove this limitation? This is a standard one, right? Starting from the feed-forward neural networks, let's go back to the early days. Traditional neural networks. This worked extremely well for problems where inputs had a fixed size. We need to feed in an input vector, it passes through layers, and we obtain an output. This worked beautifully for image classification problems, regression problems, and structured tabular data. But language introduced something different. Language is sequential, where the order of words matters the most. A common example where we see dog bites man and man bites dog. Even though they contain identical words, they have completely different meanings. So, a feed-forward network has no mechanism for understanding this sequence. Then comes the question, can a neural network maintain memory? So, the first question. Here comes the recurrent neural networks. This was introduced based on the idea of a hidden state. Instead of processing the entire sentence at once, these words were processed one after the other. Each new word updated the model's internal state. So, the current understanding became current word plus its previous understanding. So, for the first time, neural network could model its sequences. So, in that way, RNNs enabled machine translation, speech recognition, and text generation, that is a prediction of next word. So we all know that this is a huge step forward, right? But soon researchers discovered another problem, the long-term dependency problem. Suppose we have a sentence. The report that I have worked on for several weeks was finally accepted. To understand was finally accepted, the model must still remember report which appeared much earlier, right? Unfortunately, RNN struggled with the long sequences. So during training, gradients had to travel through many steps. So through these many steps, signals weakened and the information started to get faded. Most effectively, it forgot the distant context. Okay. Now the question is, can memory itself be controlled? Now, LSTMs. The long short-term memory networks. This introduced explicit memory mechanisms. So they added gates, what to remember, what to forget, and what to expose. This dramatically improved sequence learning. For several years, we have seen LSTMs dominating natural language processing. Even in NLP conferences around 2015, almost every paper contained LSTMs. Many people believed sequence modeling had essentially been solved, but another bottleneck appeared, sequence to sequence models. Here, when machine translation became popular, the architecture looked like this. First, the input sequence, next comes the encoder, then the single vector, then the decoder, and finally the output sentence. Everything about the source sentence had to be compressed into one fixed representation. For short sentences, this worked well, but for longer sentences, performance dropped. So people realize something important. Why we need to force the model to compress everything into one vector. That is where the compression bottleneck they have identified. So, instead of remembering everything, perhaps the model should simply know where the information is located. This idea changed everything. With the dynamic focus, we have the attention. So, attention allowed the decoder to revisit every encoder state instead of relying on one compressed vector. The model could dynamically focus on relevant parts of the input. When generating each output word, it could ask which words matter most right now, which means where I should turn my attention to. So, based on this, the translation quality improved significantly. Many people later argued that attention itself, that is, only the attention, not the transformers, was really the true breakthrough. Because attention removed the information bottleneck we had. But one major issue still remained, that is, the sequential computation. Even with attention, models were still based on RNNs. This meant computation remained sequential. This is the most important thing. The computation was sequential. The token 3 depended on the token 2. The token 4 will depend on token 3. So nothing could be fully parallelized. As GPUs became increasingly powerful, the sequence model could not efficiently utilize them because of this sequential nature. So the architecture itself had now become the bottleneck. Researchers had a radical question. If attention is already doing most of the important work, do we even need recurrence anymore? Because the recurrence is introducing the sequential execution. So at that time, this was absurd, but RNNs had been the foundation of sequential modeling for years. Anyhow, this idea was put into test, and in 2017, Attention is All You Need was born. The title itself was provocative. It challenged the central assumption of sequential modeling, but the paper proposed removing this recurrence entirely. Instead, every token could directly interact with every other token. No hidden state chains, no sequential memory propagation, just relationships. Every word could access every other word immediately. This architecture became the transformer. Why transformers won and what changed? Transformers provided several advantages here. Long range dependencies became easy to model, training became massively parallel and not sequential. GPUs could finally be utilized efficiently. Performance improved as models became larger. So, one unexpected thing to notice is as transformers scaled, capabilities continued improving. This changed the focus of the entire field. Before transformers, progress largely came from inventing new architectures. Every time we are getting new architectures. But after transformers, the progress increasingly came from scaling. The scaling improved the capabilities. So, the series of bottlenecks made the NLP evolution, right? Which is first the feed-forward networks, where there was no sequence understanding, then came the RNNs, but with poor long-range memory. So LSTMs came, but the sequential computation remained. Finally, when the encoder-decoder models came into action, information bottleneck was there. Then came the attention, which removes a compression bottleneck. Then comes the transformers, which removed the recurrence entirely. And this brings us to the central contribution of the paper we are about to discuss. Attention is all you need. This is why transformers were introduced. Basically, in our next talk, we will examine how the paper actually works. Thank you.